So let us look at what we term as water potential. Okay, because eventually we'll understand the direction of movement of water based on the water potential. So what is this water potential and what are the factors that influence it? Do we have a formula for it? And how do we interpret that formula? Can we do some calculations related to that formula? Perhaps in this presentation, you should be able to do that. So we start with a scenario. So you have a farmer who has noticed that in dry season, his crops will always wilt, okay, even when he irrigates them slightly. So can you define water potential and explain how it influences movement of water between cells? And then describe how a decrease in soil water potential affects water uptake by plant roots. And then explain the direction of water movement between two adjacent cells with different water potentials, and suggest one way the farmer could adjust the irrigation practices to help the crops during the drought. This is quite an excellent example of how we can apply our knowledge on water potential in growing crops, because crops will actually need water, but this water has to be applied to the crops such that they can actually absorb this water. So usually we rely on rainwater to basically enable our crops to grow. But some farmers can use different irrigation techniques to supply these crops with water. But again, if these irrigation practices are not carried out properly, the crops may not actually benefit. So that means that even when you have water, if that water is not absorbed by the plants, then you are basically not doing much. So what are the issues that we need to know? So the concept of water potential is actually very important for us to know. And that concept can be understood if we understand the three terms here. The first term is a solution. So when we are talking about a solution, we're talking about a solvent that has a solute in it. So you have a liquid component and a solute component being mixed. That's what gives us a solution. So the solvent is the liquid component, and then the other substance is the solute. It's the one which dissolves in this liquid component. So the solute dissolves into the solvent. Okay, so solute is the substance that dissolves into the liquid component, and usually it is in smaller amounts. And then the solvent, it is that substance that dissolves the solute, okay, and is the one which is usually in large amounts. So for example, if you have a beaker with water, the beaker and the water is the solvent. We actually say water is a universal solvent, because if we add sucrose to that water, that sucrose is the solute, it will dissolve in the water, and that will give us what we call a solution. So those are terminologies that we need to understand from the start. So we go into understanding the word water potential. Water potential is about the tendency of movement of water molecules. That tendency of water molecules to move is what you call water potential. Okay? It is expressed in units called pascals. Okay? Those are the units for water potential. So water potential can be indicated by the sign that, by this sign here. That sign is a Greek letter psi. Okay? So when you see this sign, it means water potential. And we have just said it represents the capacity of a solution to give out water, or the tendency of water molecules basically to move. That is what water potential means. Now, water potential, for you to understand the dynamics of water potential, just to know that pure water, that means that water which does not have any solute, no dissolved anything, no dissolved minerals, no nothing there, that is pure water. It has a water potential of 0. That means that the water molecules are not about to move. When you add solute to that water, you are making that solution's water potential to become negative. Okay? When you add a solute to a solution, you are decreasing its water potential. The water molecules will be reluctant to move out. That's what that means. So adding solutes reduces the water potential, becomes more negative. Now, water potential can be calculated using a formula where you have water potential is equal to the solute potential or the osmotic potential plus the pressure potential. So the solute potential, if we are not talking about pure water, it has to be negative because pure water is 0. You add any solute, it becomes negative. Okay? And then for pressure potential, it's usually positive. And a solution at atmospheric pressure, the water potential is 0. Those are assumptions that we can make in some of these calculations, and that the solution should be ideal. So that means that the solute molecules should not interact with the solvent molecules in any way. Those are 2 assumptions that we can make in these calculations. So we move forward. So solute potential, we're saying that if you have a dissolved particle in a solution, it lowers the water potential. And the more you add, it means the more it becomes more negative. So you have a more negative water potential. And remember, pure water has a water potential of 0. Pressure potential, this is the pressure that is exerted by the cell wall and the membrane on the cytoplasm. Remember, it is in plant cells that we have cell walls, but of course, in animal cells, we're talking about the cell membrane. But when you have water and solids in a cell, this will exert a pressure on the cell wall of the cell membrane, and that's what we are terming as pressure potential. Okay, so as the water enters by osmosis, that means that the cell is having high solid concentration, so water is moving into that cell. There is a buildup of pressure there, and that pressure creates what we call hydrostatic pressure. So it is the one that can resist entry of more water, and for plant cells, that is very important because of the cell wall. The cell wall can be rigid such that the cell cannot actually burst because of more water molecules entering it. So a turgid cell, a turgid plant cell, that means a cell which is taken in water and is here swollen properly, that cell has a positive pressure potential. So osmotic pressure and equilibrium. So that means osmotic pressure is one that prevents more more solvent molecules from entering the cell. Okay, and therefore in plant cells, because of the cell walls, you cannot have bursting of the plant cell. So the cell will be turgid in this case. In animal cells, you don't have any cell wall. the cell will take in solvent molecules, or basically water, and therefore will swell and burst because of lack of the cell membrane. So that bursting is cell lysis. Okay, so coming back to our question. So water potential is about the tendency of movement of water molecules. Okay, the tendency of water molecules to leave a solution is what we call water potential. And we are saying that if you have solids in a cell, it means that the water potential of that cell will always be negative, and the water will basically be, the water molecules will be reluctant to move out. Okay, so that's what happens. So eventually, if you have two neighboring cells of different water potentials, it means that the water will move to where you have more solute concentration. So the water will basically move to where there is a low water potential, because more solutes, less water potential. Okay, that's what will basically happen if you have two adjacent cells of different water potentials. Now, for the plants to be able to absorb water from the soil, it means that that water has to move. Okay, if we have more solids in the soil, it means that the water will be reluctant to move into the root hair. So that will be a problem. The water will basically be unavailable for the root hair to take that water. Okay, so that's what happens. So that means that more negative water potential in the soil makes it difficult for the root hair to take up that water. So you need more negative water potential in the root hair to be able to get water from the soil. That's what basically that means. Okay, and we have explained what happens to the two cells that are adjacent, with one having with the two having different water potentials. So that means that when irrigating, just know what kind of water you are basically using. If you have extremely salty water that you're using for irrigation, this water may not be available for these plants, because salty water means that you have a lot of salts, and that means that you have a negative water potential. And when you have a negative water potential, these water molecules will not be available to be taken up by the root hair. So that means that as a farmer, know the kind of water you are supplying to the plants. Otherwise, the plants, even after supplying them with water, they will not be healthy. They will wilt because of that salty content.